In our last video, we looked at the relationship between the electron and the nucleus. And I think that gives us enough information to now explore how Niels Bohr, would have viewed the atom and his planetary model. He imagined that electrons could be found in orbits around the nucleus, or sometimes these are referred to as shells. The orbit idea is why the model is often called the planetary model, where we see electrons that are um, orbiting around a central nucleus. But you could also think of it as shells. And I tend to think of like Russian dolls, the nesting dolls, where you have a big doll and inside of it smaller dolls, et cetera, et cetera. So what we're going to do is we're going to look at how Bohr identified these orbits and how he uh, what basic principles underlined these electron orbits or shells. And so to do that, we're going to start with the notion that each shell had a particular energy, and we would call that a quantized or a specific amount of energy, and that those shells could be defined by something that sounds really complicated, but in the way that we're going to use it isn't too bad. Defined by something called the principal quantum number. And the symbol that we use for the principal quantum number is n. And what you need to know is that that principal quantum number can be any integer from 1 to infinity. So 1, 2, 3, 4, 5, et cetera, et cetera, et cetera. We have a view of a Bohr planetary model on this slide. And what we're going to do is we're going to look at some of the features of his model. It's actually pretty simple. So the number one feature is that each orbit is assigned a value, a principal quantum number, with the one that is closest to the nucleus being n equals 1. And sequentially, as we move away from the nucleus, the number goes up. So the second orbit away from the nucleus is n equals 2. And you can go even further than what we've pictured here. N equals 5 is not necessarily the outermost orbit, it is just the last one we've pictured here. It could be n equals 6, 7, 8, 9, 10. You could keep going. So as n gets larger, the distance from the nucleus for that particular orbit is also going to increase. But as we talked about in our last video, that has consequences. So if I have an electron that is placed in the n equals 1 orbit, then it is very close to the nucleus. And for that reason, it's going to be lower in energy. Why? Because it has a strong attraction for the nucleus and therefore is stable, and is as low in energy as an electron can be. If I have another electron that is in a orbit that's further away from the nucleus, then by definition, it has a weaker attraction for the nucleus and therefore is less stable and is also higher in energy. So the smaller the value for n, the more stable and lower the energy that electron's going to be. So the electron is really defined by what orbit it's in. The third thing that we have is kind of new for us. It's a maximum capacity for each orbit. You can imagine that the first orbit itself is pretty small, but as you go further out, the orbits get bigger, and therefore there's more space in each orbit as we move away from the nucleus. So Bohr said that each one of these orbits could only hold a maximum of 2n squared electrons. In other words, if I look at the principal quantum number and I square it and multiply it by 2, That's the maximum number of electrons you could see in an orbit. So if I'm in the like n equals 6 shell or orbit, then that shell could hold 2 times 6 squared electrons, which is 6 squared is 36 times 2, 72 electrons go into the sixth orbit. One argument against this idea is that, electrons are very, very tiny. They're much more tiny than pictured here, and they don't take up much space. So why does the first orbit only hold 2 electrons? Surely you could fit 5 or 10 or even 50 electrons in that first orbit. But we need to remember that energy systems or systems always tend towards the lowest energy, and electrons are all negatively charged. So if we try to crowd too many electrons into the same space, they're going to repel one another. And that's an unstable situation, and it's going to be higher in energy. And so that's the real reason for limiting our orbits to a particular number of electrons. Finally, Bohr said that electrons need to go into the lowest available energy orbit first. Okay, so if I take a look at an atom like lithium, lithium has 3 protons, but it also has 3 electrons. The n equals 1 shell can hold 2 electrons total. And so we see 2 of the 3 lithium electrons in that n equals 1 shell, but we could also, or we have one left over. That third electron has to go into the second shell because there's no room in the first shell for it. Okay, so those are really the 4 main features of Bohr's model. And what we're going to see in our next video is how we can use that model to explain known phenomena. That's the real value of models, is to be able to make predictions on or explain why certain things in the universe take place. We'll see you next time.